So this is the topic for today, which is we want to analyze the typical dynamic process for the second order. This document, tutorial second order 25th April 2022, can be downloaded in the Google Classroom. So you may download and refer it to this document. So for this part, if we take a look, there are two search tanks. So the search tank are placed in series as shown in the figure 1. So in this figure 1, we have two tanks where it's located once in the series. So this is a tank number 1 and this is a tank number 2. Are initially operated at steady state with the height of first and second tank are 2 meter and 2.5 meter. So the information first if operate under steady state with the height first second tank. So this one is based on the initially. So that means the H bar for tank number 1 will be 2 meter. The H bar for tank number 2 is 2.5. So meaning that this is the height. Represent the height for the second and the first tank respectively. So both tanks are identical and have same cross-sectional area of 0.5 meter square. So in this case, we assume both tank when you have the identical, it has the same shape. So the same shape corresponding to the same area. So A1 equal to A2 equal to 0.5 meter square. So here the A1 represent the tank number 1. A2 area for tank number 2. So we just do the numbering. So in this case, we have the two tank QI coming into the tank number 1. And then, so this is the tank number 1. You have the H1 and then you have the valve. And then from the valve, we go to the Q1 and then to the H2. And lastly, exiting the tank tube using the valve R2 and Q2. So meaning that in this case, we assume the valve has a linear resistance. Linear resistance. So for example, here the R1, Q1 equal to H1 R1. So this is the standard valve linear resistance where it must be divided, the height must be divided by the resistance, where R1, the resistance, is normally considered as constant. The same goes with the tank number 2 where you have the valve. So you include the Q2 equal to H2 over R2. So this is the linear valve resistance for second tank. Now, the question asks you to derive overall transfer function relating to the height of tank 2 with the inlet flow rate of tank 1. So this is the first question. We take a look on the first question first. The question asks you to develop overall transfer function. So you need to obtain the transfer function to relate the height of tank 2, which is the H2 with the inlet of tank 1, QI. So this is the item or the property that we need to develop for this question. So in order to answer this question, then we need to have the balance. So what kind of balance that needs to be developed? So here is clearly state the height of tank 2, H2. So when it's related with the height, then that means you require the overall mass balance. So we start with the overall mass balance. So in this case, you have two tanks. So when you have two tanks, normally we will do from the left to the right. From left to the right. So that means we start with the tank number 1, and then we go through on the tank number 2. So here we develop the overall mass balance for tank 1. So here we have the MDT equal to MI minus the M1. So here we start with the mass flow rate. So in this case, the statement given is in the Q. So here it does not state what is the Q. So either the volumetric flow rate or the mass flow rate. So normally based on this, we take a look on the overall question where it state the inlet flow rate. It gives 5 meter cube per second. So it's suffice to say that the Q used in this case represent the volumetric, because the information is based on the meter cube per second. So in this case, we know that the M can be related with the density and the volume. So here we have the rho 1 Qi minus the rho Q. So normally when the question state the Q or other variable that we need to use it. So no, although in our class before, we use F as to represent the volumetric. So please do not use F, just use Q. We need to be very flexible, which is in accordance to what information has been given to you in the question. So here we have the rho1, Q1 to represent the exit flow rate tank number 1. So this equation, if we try to expand it, it becomes the rho dVdt plus V d-rho over dt. Where, based on the previous explanation, we know that the density is not going to change against time. So this one automatically 0. And we also can assume the density rho equal to rho 1 equal to rho I, which is a constant value. So this contribute to the simplification of our term, where you have the rho dVdt plus rho 1 Qi minus rho 1 Q1. So when you have the rho that's equal to rho inlet equal to rho stream number 1, then we can further reduce the equation to become the dVdt equal to Qi minus Q1. Where in this case, we can further expand. We can further relate the volume with the height. So here, the volume, in this case, I just put 1 to indicate is the stream number 1. Is for the tank number 1. So the V1 is equal to A1 multiplied with the H1. So we substitute into the equation. So you have the dA1 H1 over dt equal to Qi minus Q1. So this equation can be further represent the A1 dH1 over dt plus H1 dA1 over dt. So you have the Qi minus Q. Then In this case, on the left-hand side, we have two terms. The change of height in first tank against time, and then the change of cross-sectional area. As we know before, the area is not going to change against time. So this one will become 0. Lastly, we have the A1 dH1 over dt equal to Qi minus Q1. So this is the overall mass balance for the tank number 1. So in this case, we know that the tank number 1 here, you have the resistance valve, where the valve resistance given by this one, Q1 equal to H1 over R1. Then we can further substitute the equation inside the term. So this one become A1 dH1 over dt equal to Qi minus H1 over R1. So we already substitute the valve resistance, where this one is for the valve. Valve resistance. So once we obtain the overall mass balance for tank number 1, then the next step is of course to do the Laplace transform and so on. So here, based on the deviation variable, in this case, I just do the short form. So we have the A1 dH1 over dt equal to Q1 Qi prime minus H1 prime over R1. So this is our deviation form, where in this case, the H1 prime normally represent the H1 minus H1 bar. And then the Qi prime equal to Qi minus Qi bar. So the inlet flow rate is going to change. The level, of course, going to change. The only constant in this case will be your area A1 and the R1, the resistance. That's why in the A1, R1, you don't need to include the prime. So we have the deviation variable, then in the next step involve the Laplace transform. So we have the deviation variable. Now we go to the Laplace transform, where this equation becomes S H1 prime S minus H prime 0 equal to Qi prime S minus H1 prime S over R1. So this is after Laplace transform. The main difference is I change the small letter into the capital letter, and then I put the S bracket to indicate it has been Laplace. So the differential term you have, when we do the Laplace, you obtain the S H1 prime S minus H prime 0. So the second part, H prime 0, normally can be negated because it will represent the 0 value. So we have the equation like this, then we can do the rearrangement. Since you have the H1 on the left and the right hand side, so we can do the rearrangement. So it becomes like this. Equal to Qi prime S. We have this, then in the end, we further factorize the equation, then we can get the Qi prime S. So we have this one. So here, if we take a look, the H1 prime and then the Qi prime, this is our variable. So this is the our variable where it represent the H1 is your output. Of course, in this case, H1 represent the level. So the level represent the outcome, the variable that we want to observe in the end. So it represent our output. And then the QI here represent our input. So the next step is we want to develop the transfer function, where the transfer function based on the output divided by input. So meaning that in this case, our output will be the H1 prime S, and the input should be QI prime S. So this is the objective of transfer function development. So the transfer function we have the H1 prime S equal to 1 over A1S plus 1 over R1. So this is the transfer function to relate the output over input, where here we have the S power of 1. Whenever the S has the power of 1, it represents the first order. So now, here we want to rearrange according to the first order, where according to the first order, we need to obtain the following transfer function. The general form of first order represent the K over tau S plus 1. So in this case, we want to convert the 1 over A1S plus 1 over R1 into first order. So this, which has been explained in the previous chapter, is we try to rearrange, then you can get the R1 A1 R1S plus 1. So this represents the first order transfer function, where you have the H1 prime S over QI prime S. So this is the outcome from the tank number 1, where we get the first order. Now, the next step is to begin the second tank. So here we already complete the first tank. Then we want to begin the second tank derivation. So this means when we do for the second tank, we have all of the similar procedure like what we did for the first tank. So for the overall mass balance, for tank 2. So for this case, if we take a look, so let's say I copy this figure. Okay. So in this case, we already complete the first tank. The first tank, if we take a look, the boundary is this. This is your boundary for the first tank. So from this first boundary is cover the valve, the inlet valve at the Q1. So this resulting into the following transfer function. Now, if you want to begin the overall mass balance for tank 2, that means we need to set up another boundary, where our boundary for the second tank should be like this. So this is the boundary for second tank. Why we need to set up the boundary? In order to make sure we complete one part of the balance before we continue with another part. If we try to do it simultaneously, then it will get overlap. When you do the overlapping, then that means the equation may become imbalanced. You will not get the exact balance of the given unit operation. So this is the boundary for tank 1. So what we need to focus is, if we set the boundary, take a look on this part. So it just sitting beside each other. This boundary does not overlap. So this is the boundary between the tank 1 and the tank 2. So this means for the tank 2, you don't have any valve at the Q1. Take a look here. This is your Q1. Since the boundary setup in this case, it does not cover the valves in the Q1. So this indicates that your equation for the tank number 2 become the A2 dH2 dt equal to Q1 minus H2 over R2. So where we didn't substitute the Q1 because in this case, the boundary does not cover the previous path. So this is the thing that you need to be very clear. Based on the boundary. So for this part, if we have the A2 dH2 dt equal to Q1 minus H2 R2, this is resemble the following equation. Only this one is for applicable for the tank number 1, and that one, previous one, what I showed before, is for the tank number 2. It has the same term. The main difference is the numbering, the labeling, where this one labeling for the tank number 1, and this one is labeling for the tank number 2. So what I want to show here, that means we, in the end, we will get the similar transfer function, similar form of transfer function. So you don't need to repeat the procedure of deriving the transfer function. So here the main difference in this one will be the H2 prime S over Q1 prime S equal to, it will follow this one. R1, A1, R1, S plus 1. Only the difference, here we change to R2, A2, R2, S plus 1. So this is the transfer function for second tank. So although in this case, if you take a look, when we try to derive the first tank, it looks like that you have a lot or long derivation, long procedure. So sometimes if you can skip it, then you please skip the procedure. This one is just to as a guideline how to obtain the transfer function based on the structured way. If you already understand it, then some of the steps can be skipped. So we have the tank transfer function for second tank, and then the transfer function for first tank. So this one should be H1 Qi prime S equal to R1 A1 R1 S plus 1. So we can see, because this one represent the one inlet and one outlet, and both tanks are identical, where you have the same shape, the same cross-sectional area. And then for the exit flow rate, you both tank contain the valve. So that means the similar valve relationship will be used. The main difference may be in terms of the value of your resistance constant. So here we have the transfer function for second and the first tanks. So we take a look on the question again. So this is our equation. Derive overall transfer function relating the height of tank 2, H2 and the Qi. H2 and Qi. So the overall transfer function required for this case is H2 prime S over Qi prime S. Why I put the S? Because normally it is under Laplace transform. So that's why I put the S. So this is the equation 1. We to obtain it. So here the H2. H2 coming from, in this case, this H2. So we have the H2 in the second tank. And meanwhile for the Qi, we have in the first tank. So that is the Qi. So let's say in this case, we want to rearrange it. So we have the H1 prime S over Qi prime S. And then we have the H2 prime S over Q1 prime S. So if we try to combine two mathematical model or two transfer function, then we may get the overall transfer function. However, in this case, if we take a look, if we try to multiply both transfer function, we cannot cancel the item. We cannot cancel the variable. Although here, in the end, we consist the Qi. It consists the H2, which is the desired output variable or the desired output input variable for overall transfer function. But how to cancel the H1 and the Q1? So this is the thing that we need to cover in order to obtain the overall transfer function H2 over Qi. So for this part, we take a look on the case study again. So this means based on this, if we try to imagine, so this is the flow coming into the system, and then from the tank it will go to this before it go to this, and lastly is exit. So meaning that in this case we have the Q1, the H1, and then it will go to the R1. So note that in this case we have the transfer function H1 over Qi, and then we have the transfer function of the H2 over Q1. The one is based on the tank 1 and tank 2. So for the valve resistance, valve resistance 1. Here we have the Q1 equal to H1 over R1. So this is the valve resistance. So when we try to do the Laplace transform, this equation may become deviation variable, where the Q1 become Q1 prime equal to H1 prime over R1. And when we do the Laplace, this equation then translate to the Q1 prime S. So we just change the Q small letter into the capital letter with the inclusion of S bracket to indicate it has been under Laplace. The same goes with the height H1 prime S over R1. So this is our Laplace transform for the valve 1, valve number 1. So if we try to rearrange it, so we can get Q1 prime S over H1 prime S equal to 1 over R1. So this is the relationship for the Q1 H1 prime S. So how we can use this information into this? So again, this is our overall transfer function. So our overall transfer function here, we have the H1 over Qi, and then we have the H2 over Q1. So now we can further multiply the equation. Multiply with the Q1 prime S divided by H1 prime S. So when we include the valve relationship, then we can see from this equation where you can eliminate the H1. So this part can be eliminated with this. The Qi can be eliminated with this. So that leaves you the H2 over Qi. So the variable that we want to develop. So this means this multiplication of transfer function can be used, is applicable to obtain the overall transfer function H2 over Qi. So note that in order to make sure the transfer function are applicable, when you try to multiply it, it can cancel the undesired variable. It can cancel the unrelated variable in order to get the desired transfer function variable. So this is the thing that we want to obtain. So if you cannot cancel it, then maybe the equation is not enough. You require additional transfer function. It's like that. So for this part, since this one can be used as your transfer function, then in the end, we need to include the transfer function, where we know that here we have the H2 prime S over Qi prime S equal to H1 over Qi. We know that will be R1, A1, R1, S plus 1. Multiply with the H2, Q1 is R2, A2, R2, S plus 1. And lastly, the Q1, H1. Q1, H1, we have the further relationship 1 over R1. So we include the equation 1 over R1. So we get the following transfer function. So the next step is to do the simplification where we have the H2 prime S over QI prime S equal to. Based on this, we know that the R1 can be eliminated, can be cancelled. You have the R1 here, you have R1 here. So it can be cancelled. That leaves us the R2 on the numerator. And for the denominator, you have the A1 R1 S plus 1. Multiply with the A2 R2 S plus 1. So this is the overall transfer function relating to the second height, the height of second tank with your inlet flow rate. Any question?
Doctor,
Yeah.
does the boundary of the second tank or another tank will be always after the valve?
Yeah, normally we will set after the valve.
So we just write it without the valve resistance value, right?
Yes.
Uh, Alright, doctor.
So in this case, normally when you have multiple tanks, so normally for the our subject, the maximum unit operation or maximum tank that can be used will be 3. So here, if you have, let's say, 3 tanks, so that means you need to do it one by one. So you draw the boundary. So it's better to include the valve for the first boundary, and the second part, normally we include the second valve. It's like that. It's better to include the relationship inside our equation. Why? If we try to develop, let's say here, we set our boundary for, so this is one of the example. So in this case, we set our boundary like this. So you put the QI, and then you do it before the boundary, before the valve, before the valve. So what happened? So in this case, it's still correct. It's still okay. Only when we want to do the derivation, this equation become A dH over dt equal to Qi minus Q1. So you obtain like that only. You cannot substitute the Q1 because the boundary setup is before the valve. So this equation still okay, still acceptable because the equation has been derived according to the boundary. So for this part, normally if you want to continue it, it becomes the A dH prime over dt equal to Qi prime minus Q1 prime. So when you want to do the Laplace, it becomes the S H prime S equal to Qi prime S minus Q1 prime S. So, in this case, the way that you derive is correct. Only the problem here, you will get two transfer function, where the first transfer function, H prime, 1 over AS, Qi prime S, minus 1 over AS, Q1 prime S. So the problem in this case lie with the second. This one. Oops. Why is it become a problem? Because this is, if we take a look, this one, okay, as your output. This one is your input. But this one is your output, the Q1. Q1 cannot be your input because it's exit flow rate from the 10-1. So the location is here. So of course it becomes the output. So this is represent the problem. Because here we cannot factorize Q1 with the H. So still this one is acceptable, only you have two transfer function. When you do the second tank, then the boundary will be include this one. Then afterward, you still get the same answer, only the different way to obtain it. So both are acceptable. It will depends on the setup boundary for your work. So in this case, that's why I include the valve in my boundary, because I want to eliminate the Q1. When I eliminate the Q1, then in the end, I can get the first order transfer function. So this is the transfer function obtained for question A, relating the H2 over Qi. Where in this case, if you take a look, we have the R2 over A1 R1S plus 1 A2 R2S plus 1. So in this case, the A, you don't have any variable value. So I cannot substitute the value yet. That one is given in the case question C, where the value has been given. So we take a look on the B question. So the B, derive overall transfer function relating. Still, the question asks you to derive overall transfer function relating to the outlet flow rate. Now, they want you to obtain the outlet flow rate with the inlet flow rate Qi. So meaning that the question asks you to obtain the Q2 prime S over Qi prime S. So what is this transfer function? So this is the overall transfer function that needs to be obtained according to this question. So we can take a look on the previous, we obtained the H2 over Qi. So this is our equation. H2 prime over Qi. Now, here, we know that from the H2, we have the H2 prime S over Qi prime S. So this has been obtained according to the question A. So we have the Qi as our inlet, which is okay. Now we want to eliminate the H2. So here, the output should be the Q2. So we have the H2 here. So meaning that in this case, you require additional transfer function, which is Q2 prime S over H2 prime S. So when we have the Q2 over H2 prime S, then of course this one, if we take a look, it can be eliminate the H2. Then you get the Q2 QI. So the question, what is the Q2 over H2 prime S? How we can obtain that? So that may come from the Waf relationship. Waf relationship. So remember that before this, when we want to consider the first tank, we consider this one. Now we want to consider this one. So that one is for the tank number 2, where we have the Q2 equal to H2 over R2. So based on this, the derivation rate variable should be Q2 prime equal to H2 prime over R2. And when we want to Laplace it, it becomes Q2 prime S equal to H2 prime S over 1 over R2. Where this case can be further rearranged, Q2 prime S, H2 prime S equal to 1 over R2. So this is the valve relationship for second tank. So once we obtain that, of course, we can substitute the value. This going to this Q2 H2. So in this case, we have the Q2 over QI. When we try to multiply it, it be H2 over QI multiply with the Q2 over H2. We can eliminate H2 prime S. So that leaves us the Q2 and the QI. So where the Q2 QI is the desired overall transfer function that need to be obtained. So since this one can be cancelled, the transfer function can be cancelled each other, then we just include the overall transfer function where the H2 over QI is R2 A1 R1 S plus 1 A2 R2 S plus 1 multiply with the Q2 over H2 is 1 over R2. So in this equation, it looks like the resistance can be further eliminated. You can eliminate R2 with this R2. So that's mean in the end, the equation can be further simplified. Q2 over QI. 1 over A1 R1 S plus 1. A2 R2 S plus 1. So still in this one is the second order. So without the R2 value on the numerator. So this is the answer for question 1B. Where now, based on this, the difference, this one is the Q2 prime over QI, the overall. In this case, before this, we obtain only H2 over QI. Only up to the second height, the height of second tank. Lastly, we obtain the Q2 over Qi, where is include the valve, the flow outlet flow rate of tank number 2. So in this case, we do it one by one. And when we want to connect the tank, we use the valve as our connector. This valve relationship connecting the tank transfer function from previous tank and the subsequent tank. So when we multiply it all together, it can be related to connect the height or the outlet flow rate with the inlet flow rate. So this is the function of the valve relationship. So for this part, if we take a look further, when we have multiple tank, we will do it one by one. If we do it in the single tank, so this is our outcome. Normally, single tank, for this case, it will produce first order process. Single tank, first order process. If we put it together, like this one, if we combine both, you can see from the first order here, two first order transfer function, when we rearrange it, it becomes second order transfer function. So in this case, the second order transfer function can be obtained based on the arrangement of tank in series. Now that's how you can obtain the second order. So from these two examples, we can see we can obtain two overall transfer function, and how where we use the valve to relate the overall mass balance tank 1 and tank 2. Any question?
So if they're asking for overall mass balance in the question, we need to give like the outlet or inlet for the transfer function, isn't it?
Yes, correct. Any other question? Alright, if there is no further question, we take a break for a while before we continue with the question C and D. So we take a break. Okay, let's continue on this part. Still, we are using the same case study. So go for the question C. Now, in this case, what I want to highlight is case study 1, R1 equal to R2 equal to 4. So this is the question. So we take a look on the overall equation first, determine the gain, time constant, and damping coefficient. And then here if the inlet flow rate to the first tank. So we have the inlet, we have the information of the R. We want to find the gain, time constant, damping. Okay. And then here, if the inlet flow rate of the tank change suddenly from this value to this value, what is the height of second tank after 10 second final time? So meaning that here the question in the end we want us to find the height. So the height of second tank. So when it require the height, that means the question related for this case will be this following equation. So where this one, if we take a look, we have the height. H2 over QI. Alright, so this is the related equation that we are going to use. So this one represent the height, and then they also have the information of the inlet flow rate. And then from the question, furthermore, the question state, okay, the area is 0.5 meters square. Okay, the area is 0.5. So A1 equal to A2 equal to 0.5. So this information has been given earlier in the statement of this question. The next step is what we want to do is to substitute the value. So we have the H2 Qi prime S equal to R2. R2 in this case, R1 equal to R2 equal to 4. So we have 4 divided by A1. So we have the A1 0.5. 0.5 multiplied with the R1 is 4. S plus 1. Multiply with the A2 0.5. Multiply with the 4. S plus 1. So this one, we have the similar value of valve resistance where the R1 equal to R2 equal to 4. So this is resulting into the H2 prime S QI prime S. 4 divided by 0.5 multiplied by 4 is 2S plus 1. And then this is also 2S plus 1. Okay, so in this case, we can see on the denominator, you have 2S plus 1 twice. So this equation, if we try to expand it, it becomes 4 equal divided by 2 multiplied by 2, 4S square. 4S square plus 4S plus 1. So we take a look, here you have the S square, S power of 2. So this indicate the question is under second order. So that's how you can observe either the process in the first or second order. Just take a look on what is the higher order of the S. What is the power of the S inside the transfer function. So here although you have 2S, S power of 2 and S power of 1. But we take the higher order. So in this case, the higher order will be 2. So the form should be second order transfer function. So now, so since this one is the second order, so here we know that if you have the first order, this is the form, standard form. K over tau S plus 1, where the K is the process gain, the tau is time constant. For the second order, this is your standard form. Where, based on this, we have the K. Still, this one K is called gain, process gain. You have tau square, tau. This tau is called time constant. Still the same thing. And then for the second order, we have one additional coefficient. So this is known as psi. This one, the Greek letter, we pronounce it as a psi. So the term in this case is called damping coefficient. Damping coefficient. So here we have three terms: time constant, process gain, and damping coefficient. So here the question asks you to find the gain, time constant. The gain, time constant, damping coefficient. So what we need to do is try to compare. We have the transfer function here, H2 over Qi. Equal to 4 over 4s squared plus 4s plus 1. So we compare it with the standard form for the second order. So when we try to compare it, of course, we compare it term by term. So for example, here we know that the K is equal to 4. So here, the gain equal to 4 directly. For the denominator, we take a look. Okay, here the tau square S square. And then this is related with this one. The second term, 4s, is related to the second term. And then you have the plus 1. Plus 1. So this means both are comparable. When it is comparable in the same order, in the same form, then we can take the value directly. For example, the K equal to 4. Now, on the denominator, S square, this indicate that the tau square equal to 4. So, tau square equal to 4. So, the value of the tau equal to square root of 4, which is 2. So normally, when we do the square root, sometimes people will argue we have the plus minus of 2. However, we take notes that the tau represent the time constant. When it represent the time cannot be negative. So that means the only acceptable value for the tau should be positive value. So that's why the tau equal to 2. And then lastly, we have the second term. This one as power of 1. This one is also as power of 1. This means 2 psi tau equal to 4. We want to find the value of psi, the damping coefficient. So for this part, we know that tau is equal to 2. 2 psi, this one is 2, equal to 4. So the damping equal to 1. So in this case, this is the value of your gain, time constant, and the damping coefficient. Any questions so far?
Doctor,
Yes.
for the damping coefficient, right? May I know the actual symbol? Because it's look like 3, then I don't know how to write the
Okay.
symbol.
If you recall in the material energy balance, you know the extent of reaction?
Okay, understood. Yeah.
That is the symbol. Only in the material balance, that's the psi is used for extent of reaction. However, in the process control, the psi used for damping coefficient in the second order. So the other symbol you can refer to in the textbook. This one is the third edition. Third edition. The second order page, starting from the section 4.4. Page 66. So you can refer to the textbook. So this is the topic for today. Now, in this case, we have compared with the standard form of second order, where the standard form is the k over tau square s square plus 2 psi tau s plus 1. So based on this, we compare with the transfer function to get the gain, the tau, and the damping coefficient. So normally, in this case, once we have the value substitution, what we want to do from each equation is to do the inverse Laplace. Because if we take a look on the second question, they ask to find the height of second tank after 10 seconds and final time. So this means we need to convert the equation from the Laplace into the time domain. So how to do the Laplace? So in this case, we can refer to the page 67. In the page 67, we have a lot of the equation. We can refer it under 448, 450, or 451. So for the second order, normally, if we take a look, second order, where the second order here, normally we have the following form. K tau 1 s plus 1, tau 2 s plus 1. Or K tau square s square plus 2 psi tau s plus 1. So this is the standard form. Either on the left hand side or the right hand side. So in this case, normally for the second order, they have 3 categories. In the first order, you don't have any category, but second order, they have different category, which is depends on the value of your damping. Normally, for the damping, if you have damping equal to 1, this is what we call it category critically damped. when damping equal to 1. The category is critically damped. If your damping greater than 1, this is what we call it overdamped. And lastly, you have the zero between damping less than 1. So this is what we call it underdamped. So this is the different category available for the second order. So that's why in this case, when we get the second order transfer function, we try to find the damping factor value. So for this case, when we compare it, damping equal to 1. So when you have damping equal to 1, then this one is under category of critically damped. So when we know that our category is critically damped, then we can select the equation for inverse Laplace. Inverse Laplace for critically damped. This one, page 67, equation 450. So where under critically damped, you have the YT equal to Km in bracket 1 minus 1 plus T over tau. Exponent negative T over tau. So this is the inverse Laplace for the critically damped second order response. So that's why we need to determine the damping factor. In the damping factor, it will locate which category for our second order. So since this one is the critically damped, then this is our inverse Laplace equation. So you don't need to do the inverse Laplace manually. You just take the equation, the ready-made equation. That's why in this case, it's important to get the standard form of second order. In this way, once you obtain the damping, you can straight away take the inverse Laplace transform. So there are two ways actually to determine the category. The first one is based on the damping. And the second one is based on the value of our process. So in this case, we have the 4 over 2s plus 1 to s plus 1. So here, if we try to find the root, this part and this part. Let's say we find the root 2s plus 1 equal to 0. So you have the s equal to negative 1 over 2. And then the second one also 2s plus 1. So s equal to negative 1 over 2. So the s here, the value of the s represent the roots. The answer for the s, the possible for s value if we equivalent it to the 0. So based on this, you can see the root are similar. When you have the root similar root, two similar roots, then it is automatically under category of critically damped. So where the roots are equal. So this is based on the roots. So here we directly know when you have the same root normally you have the same tau 1 and tau 2. So for example here, tau 1 equal to tau 2. Then automatically the root are equal. So for this part, if we take a look, we have 2s plus 1, 2s plus 1. Tau 1 is 2, tau 2 is also 2. The same root will be obtained. That means confirm your process is under critically damped. It's like that. Now, once we obtain the inverse Laplace, so this is our inverse Laplace. So here, this one is the general equation. So we can put it into perspective. Here, our equation will be the height of second tank. So that means we put the H2 prime T equal to K. The K in our case will be 4. M is for the magnitude. So the magnitude based on your input. So when you take a look, the input for your case, this one, inlet flow rate for the first tank change suddenly from 5 to 6.5. So the magnitude here, M equal to 6.5 minus 5. The inlet flow rate, 6.5 minus 5. So 6.5 minus 5. And then 1 minus 1 plus T over tau. Tau is equal to 2. Exponent negative T over 2. So this is the substitution of variable inside the equation for inverse Laplace. Critically damped second order. So the next step, the question wants you to find height, 10 seconds. Height of second tank after 10 seconds. So we substitute. Here we H2 prime, we put 10. So this one for 6.5 minus 5 is 1.5. 1 minus 1 plus 10 over 2. Exponent negative 10 over 2. Alright. So we already substitute the value. Then of course you can straight away calculate the value of the right hand side. So please calculate it for me.
Doctor, 5.76.
Again,
5.76.
5.76. Okay, please others confirm the answer for me. Do you get the same
Yes,
answer?
the same.
All right, thank you very much for your response. So now we have the answer of H2 prime equal to 5.76. We know that the H2 prime is your derivation variable. It represents the H2 prime equal to H2 minus H2 bar equal to 5.76. So in this case, if we take a look again, the H2, based on the information given, so this is our information. Height for second tank 2.5. So this is the value. 2.5 meter. So we substitute the value of the H2 bar. H2 minus 2.5 equal to 5.76. And lastly, H2 equal to 2.5 plus 576 equal to 8.26. So this is your height after 10 seconds. Any question? Okay, if there is no further question, then we continue with the remaining question. Now we already calculate the H2 at 10 seconds. And lastly, the question asks you to calculate at final time. So in this question, the final time is not given. So because we have only this statement, they just give you the value of the resistance, gain, time constant, damping, inlet fluid change, the magnitude. The first time is 10 seconds, which has been used. And lastly, it just indicate the final time. So for this part, if the time specifically not given or is referred to the final time, then this time refer to the t equal to infinity. So sometimes when the time is not given, it just asks you to calculate value at final time or value at new steady state. Then it's referred to the time equal to infinity. So for this part, we still use the same equation. So now the time is at final time. T equal to infinity. So we just change the t with the infinity, where this one has to time infinity minus equal to 4, 6.5 minus 5, 1.5, 1 minus 1 plus infinity divided by 2, exponent negative infinity divided by 2. So this is the value substitution. So what is the answer on the right hand side?
6.
Will be 6. All right. So again, we just repeat. H2 prime equal to H2 minus H2 bar. So H2 equal minus 2.5 equal to 6. Then your H2 is actually 8.5. So this is the final height. So the ultimate height that can be obtained when you operate the system until final time. In this case, time equal to infinity. So when we try to observe the behavior, so let's say this is your graph for the H2 against time, where you start at 2.5. So this is time 0. When time 10 seconds, it get to the 8.26. Then 8.5. So this is time equal to infinity. So that means if we try to just sketch, the process has been reached the steady state and then maintain. Like that. And this value, the maximum height that can be obtained should be 8.5. So it is impossible to get more than 8.5 for this case. So this is what we call it problem solving. So we start with the derivation, we obtain the single transfer function, we multiply it to get the overall transfer function. And once we get the overall transfer function, we identify the order, first, second order. If second order, then you have additional characteristic to determine which category for second order, where normally the second order consists of 3 categories: critically damped, over damped, and under damped. So for this question, since the tau 1 and the tau 2 is equal and similar, then automatically it is fall under critically damped. Or if we try to recalculate it, the damping coefficient equal to 1. So for this part, once we select the category, then we can obtain the form of inverse Laplace. So based on this inverse Laplace, we get the answer. The height at the time equal to 10 seconds and the final time. So we go for the last question, the second order again. Only in this part, if we take a look, the value of the R is different. R1 equal to 4, R2 equal to 6. The remaining question is still similar. Only I change the value of the resistance to illustrate how the equation can be further changed. So still we use this equation. So this equation H2 over Qi, only here we can substitute the value of the R1 for R2 equal to 6. So this means your equation become one still 4. R1 is 2s plus 1. And then the A2R2 will be 6 multiplied by 0.5, 3s plus 1. Okay. Now, based on this, you have 2 tau. So this is the first tau, tau 1. This is tau 2. So where the roots, if we take a look, 2s plus 1 equal to 0. So s equal to negative 1 over 2. And second one, 3s plus 1 equal to 0. So s equal to negative 1 over 3. So in this case, you can see there are 2 roots. S equal to negative 1 over 2 and s equal to negative 1 over 3. When you have 2 roots and then you have unequal, or you have 2 different roots. 2 different roots. So based on this, it is automatically the class is over them. That's how we can decide based on the roots itself. So if we want to, this is the first approach to determine the second order under which category. The second, of course, using the damping coefficient. So for this part, this one can be extend for 6s squared plus 5s plus 1. Where of course we know that the second order should be k over tau square s square plus 2 psi tau s plus 1. So we just compare it directly where the k equal to 4. The tau square equal to 6. 2 psi tau equal to 5. Like that. Where based on this, the tau square equal to 6. So the tau should be 2.45. So the tau square equal to 6 and the tau should be tau equal to 2.45. When we substitute it, 2 psi 2.45 equal to 5. So the damping equal to 1.0206. So here we know that the damping is greater than 1. So based on the damping, when the damping greater than 1, it is over damped. So it's like that. So in this case, once you obtain the damping greater than 1, so that means we can take the inverse Laplace equation. For this part, you can take equation 448 page 67 for overdamped response. Where in this case, the overdamped response, here you have the YT equal to Km. Then you have the bracket 1 minus tau 1 exponent negative T over tau 1 minus tau 2 exponent negative T over tau 2 divided by tau 1 minus tau 2. So this is the inverse Laplace for overdamped system. So for this part, then we just substitute the value. Where here we know that the YT is the H prime T. K is 4. M, the magnitude 5, 6.5. So M equal to 6.5 minus 5, which is 1.5. So we get 1.5. And then 1 minus tau 1. Tau 1 is, if we try to locate it, tau 1 is equal to 2. And tau 2 equal to 3. So for this case, normally it based on your order. It's okay to have the 3 as the tau 1, then the 2 become your tau 2. It's like that. If you miss up, still okay. As long as you locate at the right place. So this one, I refer tau 1 is equal to 2, tau 2 equal to 3. Or maybe in your case, sometimes maybe you want tau 1 equal to 3. So automatically tau 2 equal to 2. So that one is based on your selection of the tau. So the order is depends, we decide which tau is belong to. So here the tau 1 equal to 2, tau 2 equal to 3. Tau 1 equal to 2, exponent negative t over 2 minus 3 exponent negative t over 3. Then 2 minus 3. Okay. So in this case, the question asks you to find the height of the second tank. So the height of the second tank, h prime at 10 seconds. So what is the answer? You just can calculate it. 1 minus 2 exponent negative 10 over 2 minus 3 exponent negative 10 over 3 divided by 2 minus 3. So here you can directly calculate.
Doctor,
Yeah.
Doctor, in this question, the R2 value is given as 6. So we have to consider that 6, right?
To value of 6, which means
So the equation in starting, the R2 value should be 6, right?
R2 value in this case. R2 value should be 4, right? Oh, sorry. Yeah, you are right. I'm sorry. I mistake this one. Thank you. So this is not 4. Yeah. Because the R2 is equal to 6. All right. Thank you for correcting me. I didn't notice it. So the K equal to 6. Okay. So 6 multiply 1.5 should be 9. So this is 9. Okay. All right. Thank you for correcting me. I didn't notice it. So here the R2 is equal to 6. So when we multiply with 1.5, it becomes 9. So what is the value of the H prime 10?
Eight point 16.
8.16. Okay, somebody please check your friend answer.
Yes, Doctor, same.
Okay, thank you. So to obtain the right the actual height, so you add with the 2.5, which is resulting into 10.66. So this is the value of height at 10 seconds. And lastly, for the height at infinity, you just change the t with the infinity. So for this part, I believe h2 prime infinity is equal to h2 minus h2 bar, where h2 minus 2.5 equal to time infinity. So will be equal to 9. So H2 equal to 11.5. So this is supposed to be the answer at time infinity. The height of second tank at time equal to infinity, and this one is 10.66 at the time equal to 10 seconds. You get the same answer?
Yes, doctor.
All right. So for today class, what I want to emphasize is the second order, where the second order has different class. So for today topic, I illustrate using the multiple storage tank to get the second order process, where depending on the final transfer function, depending on the value of resistance, you can get either overdamped or critically damped. So this choice of the category in the end decide which inverse Laplace transform should be obtained. So this is the tutorial that I think is very useful for you to illustrate or to practice. Rather than I go through the theory, then I think this is the better way to understand it, how to apply, how to obtain the second order, and how to solve the problem relating the second order. So for now, we already covered the overdamped and critically damped. So this has been covered. So that means we have the damping equal to 1 and damping greater than 1 for the overdamped, where the roots, different roots. So for Wednesday class, we will cover the underdamped response. So this is the second part for the second order. So I open to any last question before we end our class for today. So if there is no further question, then I think we end our class for today. So on behalf of myself, I would like to say thank you again for your attention, for your response for today's class. Then I meet you online again on Wednesday. With that, thank you very much. Have a nice day. Class is dismissed.
Thank you, doctor.
Thank you, Doctor.
Thank you, doctor.
Yes,